In a previous lecture, we had studied wave propagation in one dimensional continuous media governed by the wave equation, and we have looked at propagation of general waveforms as well as harmonic waves. Today, we are going to discuss wave propagation in beams. So, let us first look at the equation of motion of a Rayleigh beam. So, this is the Rayleigh beam model. Now, when we talk of wave propagation, we would be interested in propagation in an unbounded medium. So, we do not consider any boundary conditions for the moment, assuming that either the boundaries are too far off or the time interval in which we are looking at this phenomenon is very short. So, we are interested in looking at propagation of harmonic waves which we will represent in the complex form . So, we would like to look at the propagation of waves of this form, where this k is the wave number lambda is the wavelength and omega is a circular frequency. Now, we have discussed previously that so this is the form of harmonic waves. So, it has got two parameters k and omega and the amplitude d. Now, when a harmonic wave propagates in a medium, for example, string or here a beam, then this k and omega can no longer be independent variables. So, they get coupled. So, let us see that coupling. So, when we substitute this in the equation of motion, so we will obtain this relation between omega and k. So, this here I have simplified, I have substituted in here and simplified by removing the exponential term. This is known as the dispersion relation. So, this relates the frequency and the wave number of the harmonic wave that can propagate in the Rayleigh beam. Now, we will simplify this a little bit. So, if we define omega tilde as omega times r g over C L, where r g is the radius of gyration of the cross section, and C L is the speed of axial waves in the beam, and we also define k tilde as r g times k. So, with this definitions of omega tilde and k tilde, the dispersion relation can be written as So, this is our dispersion relation represented in terms of omega tilde and k tilde, which are non dimensional frequency and wave numbers. Now, in the case of an Euler-Bernoulli beam, for an Euler-Bernoulli beam, this relation which implies that so this is the dispersion relation for the Euler-Bernoulli beam. Now, we have seen before that the speed of propagation of the harmonic wave is, which is known as the phase speed. So, the phase speed or phase velocity is given by omega over k. So, that is the phase speed or phase velocity of a harmonic wave in a medium. Now, if we calculate the phase speed in a Rayleigh beam, for example, so we will write as so if you use the expression of omega tilde and find out this ratio, then we have the phase speed, it is plus or minus, but then it represents the speed in the positive and the negative directions. So, the phase speed is k tilde over under root 1 plus k tilde square. So, and similarly for the Euler-Bernoulli beam, it is given by just k tilde, because omega is plus minus k tilde square. So, omega over omega tilde over k tilde is just k tilde. So, this indicates that as k increases, the phase speed in an Euler-Bernoulli beam increases linearly with the wave number. So, waves with higher wave number, which means shorter wavelengths, will propagate at higher speeds in an Euler-Bernoulli beam, and this increases as k tends to infinity, Cp tends to infinity. But if you look at for the Rayleigh beam, then so as k becomes very large, it is much larger compared to 1. In that case, this becomes negligible. So, it is under root k tilde square. So, this becomes 1. So, Cp is bounded, whereas in an Euler-Bernoulli beam it becomes unbounded. Now, this is unphysical. So, we can understand that in an the Euler-Bernoulli beam represents an unphysical model when the wave lengths become very small, which means wave number goes to infinity. So, for very short wavelengths, they can travel at infinite speed. So, as the wavelength goes to 0, the speed goes to infinity, which is quite unphysical. Whereas, in the Rayleigh beam this is bounded, and the reason it is bounded is that is the presence of the rotary inertia term. So, you can see the important role played by the rotary inertia term in a beam model. Now, because of this infinite phase speeds, something very strange or peculiar can happen in an Euler-Bernoulli beam model. So, suppose you disturb the beam at a particular point, then the effect of the disturbance can be felt at infinite distances from the source of disturbance, because shorter and shorter wavelengths. Because if you, for example, give an impulse, then you are giving a disturbance of all possible wavelengths. An impulse is represented by all possible wavelengths. It is a combination of all possible wavelengths, because its Fourier transform is 1. So, all possible wavelengths have equal contribution in the impulse. Now, since for very high wave numbers, so very short wavelengths, the speed is infinity. So, you can feel the effect of that impulse at large distances, at infinite distances in an Euler-Bernoulli beam, which is quite unusual. So, it is quite unphysical that way. So, Rayleigh beam is a in that way a better model for the beam. So, this is because of this rotary inertia term. The other thing that you must note here, you see the wave speed is a function of, in both cases the wave speed, the phase speed is a function of the wave number. So, what this means is that if you have a collection of harmonic waves constructing a wave pulse or a waveform, and when this waveform propagates, since different wavelengths are propagating at different speeds, so obviously you expect that see the initial wave pulse or the waveform is constructed using these individual harmonic waves in a certain manner. Now, suppose some waves travel at some speed and some other waves travel at some other speed. So, different waves are traveling, different wavelengths are traveling at different wave speeds, then this combination, the combination of all these harmonics is going to change the waveform. So, the waveform changes as it propagates. This is known as dispersion. So, we have dispersion in when a wave pulse propagates in a beam. So, this is an effect of dispersion is change of waveform. So, when you have dispersion, the waveform changes. This is an effect of that of dispersion. Now, here let us look at this dispersion relation of the Euler-Bernoulli and the Rayleigh beam models. So, you can so this I have plotted omega tilde versus k tilde. So, you can see that this is quadratic in k tilde, as we have seen. Omega tilde is k tilde square, whereas this tends to a line. So, with a certain slope, and omega over k becomes finite. So, this is the Rayleigh beam and this is the Euler-Bernoulli beam. Now, so we have looked at this dispersion relation, and now let us calculate the waves that can propagate in the beam. So, for that we are going to once again, so let me write down the dispersion relation once again. Now, so this dispersion relation can be used to solve for k in terms of omega. So, let me, so if you do that, so if you solve for k, so the non-dimensional, so we will solve for k tilde. The non-dimensional dispersion relation was so we had converted into non-dimensional form. So, if you solve for k tilde, you obtain two values. So, you can see this is a quadratic in k tilde square. So, you have two values for each k 1 and k 2. So, these are represented, I am representing them as I beta 1 and beta 2. So, here beta 1 is and beta 2 which you can very easily find by solving this and representing. So, I am representing this k 1 and k 2 in this using this beta 1 and beta 2. So, then finally, if you represent the full wave solution, so you have these 4 solutions of k tilde. So, there you have 4 terms in the solution. So, this represents the waves that can propagate in the beam. So, as per the solution of the wave number in terms of the non-dimensional frequency omega. Now, if you look carefully at these solutions, then you find that these 2 terms. So, this term and this term, they actually do not represent any travelling wave. They are not actually travelling wave. They are, in fact, this is decaying in the positive x direction and this is decaying in the negative x direction. So, if you actually have an infinite beam, then these 2 solutions, these 2 terms actually will not exist. So, these terms can exist, of course, when you have a boundary or when you have an obstacle or a beam interacting with something external element, maybe a massive element or a stiff element. So, whenever you have interaction of the beam, then these terms can appear, otherwise these terms in an infinite beam, these terms cannot be present. These are actually, as I mentioned, are not travelling waves, they are called evanescent waves, they are decaying or evanescent waves. They are, though they are called evanescent waves, they are really not travelling waves, or they are also called near fields. So, they exist near a boundary or a mass point or an interaction point. So, they can exist only close to a boundary and their amplitudes will fall off. So, this will fall off in the positive x direction, this falls off in the negative x direction. Now, let us look at scattering of waves, in which we will now have an opportunity to look at these evanescent waves or near fields. So, now, one more thing before we proceed. In the case of the Euler-Bernoulli beam, you see k the dispersion relation was omega square is k power 4. Now, here therefore, we will have solutions of k. So, k square is plus or minus omega tilde. Therefore, k tilde So, again you have 4 solutions. The only thing is here, suppose I call them as beta, then I have plus or minus I beta and plus or minus beta. So, both are so there is no beta 1 beta 2 as in the case of a Rayleigh beam. In the Euler Bernoulli beam it is just beta. Now, we are going to look at scattering of waves in an Euler Bernoulli beam. So, let us consider this semi infinite beam So, this end is connected to a linear spring of stiffness K L, and a torsional spring of stiffness K M. So, let us consider that there is an incident harmonic wave represented by So, we have an incident harmonic wave in this form, and when this is incident on this boundary which has these stiffness elements, there will be a reflected wave, a reflected harmonic wave, which we represent as so let me put this let me call the wave numbers at present k 1 for the reflected incident and reflected, and there will be now an evanescent wave which we will represent in this form. It is a decaying wave in the negative x direction. So, its representation would be so we have an evanescent wave which is decaying in the negative x direction. Now, therefore, the total wave field in the beam, so you will not have an evanescent wave with negative x, since as the beam goes up to minus infinity, such a wave would diverge. So, from physical considerations we have only one evanescent wave in this form. Now, so the total wave field is given by now here we have dynamic boundary conditions. So, at this end of the beam we have two boundary conditions. Because of this linear stiffness we will have a shear force condition, and because of this torsional stiffness we will have a bending moment boundary condition. So, these may be represented as where this alpha m is nothing but K m, the stiffness of the torsional spring, the torsional stiffness over E I. So, times the slope that is going to give the moment, and similarly the shear force condition So, this is K L over E I. So, there is a positive because the relation between moment and shear force there is a negative sign. Now, here we so we have finally the boundary conditions which are dynamic boundary conditions. Now, we substitute this wave field or the wave fields wave form solution in the boundary conditions, and we will try to compute these coefficients B and C in terms of A, because A is the incident wave which is, so A is known. So, in terms of A we would like to know B and C, which means the amplitude of the reflected harmonic and the reflected evanescent waves. So, if you do that, and consider that the this is an Euler-Bernoulli beam. So, you have two equations. So, these are the two equations obtained from the bending moment and the shear force conditions. Now, these are two simultaneous equations in B and C. So, you can solve for B and C in terms of A. So, we will solve this as a ratio. So, B over A, which we will call the coefficient of reflection for the harmonic wave, and that is obtained as so this is the expression for the reflection coefficient as it is known as. And similarly, you can find out the reflection coefficient of the evanescent wave, which is C over A as So, here you have to substitute this expression of B over A or the C reflection of the harmonic wave. So, once you do that, you can solve for the reflection coefficient for the evanescent wave. Now, we can consider various special cases. For example, you can consider the pinned end. So, when the end is pinned, we can consider that. So, here if this end is pinned, so we have infinite stiffness for the linear spring and 0 stiffness for the torsional spring. So, in other words, this is alpha L, this is alpha m. So, in that case, if you substitute this, make this take this limit in these expressions, then you obtain so if you which means that the harmonic wave is reflected with a phase inversion. So, phase change of pi, whereas there is no evanescent wave, no evanescent wave reflection when a harmonic wave is incident on a pinned boundary. The next case could be a fixed end, in which case both of them tend to infinity, and in this case the reflection coefficient for the harmonic wave is this, and for the evanescent wave is given by this. So, now you have, this introduces a phase in the reflected harmonic wave, and also you have additional another phase in the evanescent wave. You can have further conditions. For example, if you consider sliding end, which means that alpha L is 0. So, linear spring is 0, whereas the torsional spring is infinite. So, in that case the reflection coefficient for the harmonic wave is 1 and the reflection coefficient of the evanescent wave is again 0. So, we see that now there is no phase inversion, the phase change is 0. So, the wave will get reflected without any phase change, and there is no evanescent wave generated because of this. Similarly, you can study a free end where both the stiffnesses vanish. So, there is no linear or torsional stiffness, then again you can find out these coefficients, the reflection coefficients for the harmonic and the evanescent waves. Next, we look at when the situation when a harmonic wave is propagating in a beam, and we want to look at the motion of the material points on the, let us say, the top surface or the bottom surface of the beam. So, we are interested in the motion of the material points on the surface of the beam when it carries a harmonic wave, a propagating harmonic wave. Now, this problem is interesting because it has led to a number of applications, especially in ultrasonic motors. So, this is used in ultrasonic motors in a certain way. So, let us look at motion of material points in a beam. So, consider this So, this beam element so we consider a and when this gets deflected, so this distance, so P was a point on the top surface of the beam in the undeflected position, and when this gets deflected, this point moves to P prime. So, the axial motion of this point because of the deflection may be written as, for small deflections it may be written as del w del x is the small angle and times h by 2. So, the small angle times this height will be the axial motion of this point P. Now, then I can write this vector, this position vector P, so this location was x. So, this location was x. Now, this is x minus so this is the x coordinate of the point P prime and the z coordinate. So, this was the initial z coordinate, so that is the position vector. Now, once we have the position vector, we can write down the velocity by differentiating the position vector So, that is the velocity vector. Now, suppose you have a harmonic wave propagating in this beam. So, this is the representation of the harmonic wave. Now, if you substitute in the position equation, then you obtain. So, if you write this as p x I cap plus p z k cap, then you obtain p x as and p z as So, this is the one is p x, the other is p z, these two coordinates. So, from here we can very easily see that these satisfies the So, this is nothing but the equation of an ellipse. So, which means that this point P actually traces out an ellipse. So, its location, the center of the ellipse is x and h by 2. So, actually it is it's in this form. So, and you can find out its semi major and semi minor axis. So, the point traces an elliptic path at centered at x and h by 2. So, now this, if you now look at the beam, with let us say a rigid body on top of it, which is pressed down upon on this beam, and this beam, if it carries a wave, in this direction, then from the velocity expression you can easily find out that velocity of these points on the top of at these crests, the velocity is in the negative direction. This can be found out by looking at the velocity expression, and this velocity set on the at the crests. So, if you have a rigid plate or a body in contact with these points, then it is going to be transported with this velocity. So, to just recapitulate what we have discussed today, we have looked at wave propagation in beams, we have looked at the dispersion relation and the wave propagation characteristics of the beam in a beam, and we have seen how a Rayleigh beam is a better model than an Euler-Bernoulli beam. Finally, we have looked at scattering of waves in a beam and the motion of material points of the beam. So, with that we conclude this lecture.